Hey, this is 9.2, the second conic section. We're looking at the hyperbola. First, we'll go ahead and define the thing. The hyperbola is a set of all points such that the distance from a point on the hyperbola to the focus minus the distance of one of the, well, it's a general point, right? So long as the point in the plane satisfies this relationship, and that the difference between its distance to the second focus and the first focus is equal to this 2a value, then you have it. So I know that's kind of cryptic, so let me give you a picture. So it's a lot like the ellipse in that you have two foci floating about. So you're going to have vertices again and foci. The weird thing about the foci here is that the foci are on the outside of the vertices. Okay, so for instance, maybe foci 1. It still has the same letters associated with it. So focus is located at C units away from the center of the picture. So this will be at C, 0. The vertices located at position A units away from the center. Okay, and then likewise for the other direction. This time they're going to, instead of the major axis and the semi-major axis, there's a transverse axis, which is the horizontal in this case. And then they have the conjugate axis, which is the vertical axis. Okay, so this axis is the conjugate. Right, so the vertices are always going to be on that transverse axis. The sort of vertices on the conjugate axis will be given the letter B again. Okay, so this will be located at 0B. This is located at 0, negative B. So we don't even have any of the picture going yet, but the way you're going to do it is kind of like draw a box. Okay, so let me draw a box in red. And you base the box on the A and B values. And then through the corners of the box, you're going to draw these asymptotes. Okay, so I guess I'll put those in blue. And the asymptotes kind of direct the picture of our hyperbola. And the hyperbola basically is just like two parabolas, I guess it looks like. So let me draw finally the actual hyperbola. It has two branches which conform to the asymptotes. So they get closer and closer to the asymptotes as we go towards positive or negative infinity. Okay. So it'll look, that's the actual graph then, or just those two kind of parabola-looking things. Yeah, so I mean that's kind of the picture in this case. The formula for this thing will be, again, it's a lot like the hyperbola. Sorry, it's a lot like the ellipse, but instead of the plus, you have a minus in between the two terms. So it's kind of easy to remember. Just put a minus there instead of the plus. Okay. Again, we have to worry about different orientations. So this is one orientation. Then, of course, you could have the transverse axis on the y-axis. Okay, so here again, we'll draw the vertices and the foci, and then put the b values on. Now, the x-axis, which is now the conjugate axis, and the y-axis is now the transverse. So again, if you were to draw this, it's like the first step is kind of just to get all those points plotted. Then you want to do your box, and then draw the asymptotes through the corners of the box, like this. And then you could draw your branches, and in this case, branches will go on the y-axis, looking like this, conforming to the isotopes. And our formula for this orientation, y squared over a squared minus x squared over b squared equals 1. Okay. In this case, unlike the ellipse, the a and the b values don't have to have a relationship between them. Like for the equation of an ellipse, the a value is always greater than the b value. But for the equation of hyperbola, that relationship doesn't hold. And also the relationship between a, b, and c is different. That relationship will now be c squared equals a squared plus b squared. And so c can be found by taking the square root of the sum of the a squared and the b squared. What else? The isotopes. So the isotopes, once you figure out the a and b value, are kind of done for you. Because the a and the b will determine the slope of the isotopes. So looking at the first picture, the blue dashed lines, those are your isotopes. And let me just kind of color one in yellow. Okay, so here's one of my isotopes. So in order to do the equation of a line, you need two things, right? You need a point, and in this case, the point is just 0, 0. Okay, so that's kind of the center, if you will, of this picture. So you'll have a point, 0, 0, and then you also need a slope. And what I was saying is that the slope is just determined by the a and b value. So you notice the rise over run for this line. You go up by b, and then you go and run by a. So the slope will be up by b and then run a. So in your point slope form, you got y minus y1 equals m times x minus x1. And you're plugging 0, 0 in for the y1 and the x1, and so you'll just end up with y equals b over a x for your one of your isotopes, right? And then the other isotope, if you allow me to, I'll do that in yellow now as well, is just the negative version of that slope. So to get the slope of this one, you go down by b, and then you run by a. So the two isotopes then at the end of the day, so you have one there, and then the other one found by going m equals down b, so negative b over a. And the formula at the end of the day will be y equals negative b over a x. Okay, it's the same sort of spiel over here with the other orientation. It's just, okay, let me label this. This is the isotopes. The other orientation then is the same construction for the isotopes. It's just over here, your slope, instead of having to go up by b, because of the orientation now, so this point right here on the vertex would be at 0, comma a, right? And then this point on the conjugate axis is b, comma 0. So the slope is different, right? So if you just take this, I'll do it again in yellow. If you take this first isotope here and you want to know its slope, you would have to go up by a now and then over by b. So it's just the reciprocal of the other slope. So at the end of the day, you're going to get two isotopes, again, y equals plus or minus b all over ax. Right? I think I forgot an x over here. I'm going to have to write over that, sorry. Okay. So there's a lot to, there's a lot of stuff going on here. In general, I probably wouldn't worry too much about the isotopes. Like in real life, if I took another math class, there's a good chance you're not going to worry about the isotopes too much. Yeah, but anyways, what we want to do now is actually just work with graphing these things, and see how that goes. Maybe I should note what the foci and everything are, the locations of the foci. Would that be a good thing? So if you're doing some notes here, the center is 0, 0. The foci will be at plus or minus c comma 0, and then the vertices on your transverse axis, I'll say v sub t, will be at plus or minus a comma 0. And then the I guess, quote unquote vertices, they're not even part of the graph anymore, but the points on the conjugate axis, I'll say v sub c, will be at 0 comma plus or minus b. And then likewise for this graph here, except with everything reversed. 0, 0. The foci will be at 0 plus minus c. And the vertices on the transverse axis are at plus or 0 comma plus or minus a. And then the vertices on the conjugate axis will be plus or minus b comma 0. Okay. Okay. So yeah, a lot going on there. Let's go ahead now and take a look at maybe some graphing this orientation, and then we'll worry about the hyperbola oriented anywhere in the plane, and then we'll do some complete the square problems, and then we have one application to look at. Okay, okay. So graphing centered at the origin. Usually I give written in class tests for this. You'll be taking it on my math lab though. Usually I have sort of a program I want you to follow. I would want you to locate the vertices. In other words, get the A, B, and C value. Secondly, draw your rectangle. And of course, label, also put points down for the foci. Okay. And I realize the C value is not a vertex. That's for labeling the foci. Thirdly, then just draw your asymptotes. On a test, I wouldn't even ask you for the equations of the asymptotes, but I know in my math lab they do ask, so I have to kind of just go through that a bit. And then lastly, draw your branches. Okay. What applications do these things have? Again, modeling orbits and trajectories of satellites, so things in outer space. Also, believe it or not, working in 3 dimensions, so to identify sort of algebraic equations that have this kind of polynomial type look to them. You can, when they have multiple variables, you can graph them in 3 dimensions. Okay, and when you graph them in 3 dimensions, well, it's kind of hard to draw that. So what you do is look at the cross sections. Like if you ever played Fruit Ninja and you chop a orange in half, and you look at the 2 halves of the orange, and they look like circles. You kind of do that. You'll chop 3-dimensional objects by kind of letting one variable equal 0, and then you look at the cross sections, and from that you can construct the 3-dimensional object without having to draw the thing, I suppose. So it's important there. That would be in Calc 3 if you kept taking math. If you're going to be an engineer or something like that, you would see that. Okay, so lots of applications. This isn't just something we're beating you up over for no reason. Anyways, let's go ahead and take a look at a graphing problem. So we have x squared over 9 minus y squared over 25 equals 1. And first thing, I want to get the A, B, C values. So the A value is whatever is positive, whichever term is positive. That's where so it's no longer about which one is bigger. Okay. So in this example, if it was an ellipse, you would say, well, the A value is 5. But with the hyperbolas, no, you don't play that game. The A value is with whatever is positive. So look at the formulas over here. The A goes with the positive x squared. Over here, the A goes with the positive y squared. Okay, so that's how you play that game. So A here is 3. B is 5, and then our C value is the square root of 9 plus 25, which is a square root of 34, which is about 5 point something, 5.83. Right, so let's go over and now sort of plot these points. The transverse axis is on the x-axis this time, so we will put the foci and stuff there. 1, 2, 3 for the vertex, 4, 5, 6 for the foci, 2, 3 for the vertex, 4, 5, 6, and then the foci in there. And then up and down, 1, 2, 3, 1, 2, 3 for those guys. So as you go, you can kind of, you know, if the computer asks for it, there's the center. The foci will be at plus or minus root 34, comma 0. The vertices on the transverse axis will be plus or minus 3, comma 0. Vertices on the conjugate axis, plus or minus 5, comma, 0 plus or minus 5, sorry. Okay, right, so let's go ahead and draw our box. I'll do that in blue. Get your isotopes going through. I'll put those in red. Okay, the equations for our asymptotes, if they ask, and I don't think they always ask, but sometimes they do, it'll just be y equals, for this orientation, you're going up by b, up or down by b, and then over by a. So it's going to be plus or minus 5 thirds times x. And then what else? I got to draw the branches. Okay, so a lot of work to get one of these things. It should go through the vertex there. Okay. Right. So I think that's. Whoops. You didn't go up. I didn't go up by 5 for the. I apologize. So for. Sorry. Sorry. So here we go. 1, 2, 3, 5, 6. 1, 2, 3, 2, 3, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. I only went up and down by 3. I apologize. Get your box. Get your isotopes. And then go ahead and do your branches. Swoop. Not the best drawing in the universe, but I think you get the picture. Okay, let's go on another one. So let's look at 23. 9y squared minus 25x squared equals 225. Right, so this one is all jumbled up. This is kind of, it doesn't look like it's in the appropriate form, in other words. So you need a 1 on the right-hand side, so divide everything by 225. You'll end up with 9y squared over 225, which is the same as 1 over 25 if you reduce, minus 25x squared over 225, which is the same as x squared over 9, and then you have 1 over there. Okay, so in this case, the a value is 5, the b is the 3, and the c is the square root of 25 plus 9, which again is square root 34. So about 5.83 again. Okay, so the y is the positive, the leading term there. So in this case, the transversal axis will be on the y-axis. And 1, 2, 3, 4, 5, 8 something. So there's our focus and vertex. 4, 5 something. You can go ahead and get your formulas while you're doing this. Center, or the points, center is 0, 0. Transversal is 0, comma, plus or minus 5. The foci, 0, comma, plus or minus root 34. And then vertices on your conjugate axis, plus minus 3, comma, 0. Okay, so 1, 2, 3, 1, 2, 3. Then we need our box. So as usual, I'll do that in blue. I didn't label that vertex. Should be right there. And then we do our transversals, or sorry, our asymptotes. Those should go through the corners of the box. Usually need formulas for those guys. Okay, so y will equal plus or minus. In this case, we're going up by a and then over by b. So a all over b x. And finally, then draw your branches. Make sure you put them on the appropriate axis. So this time the transversal is on the y-axis. So that's where your branches go. Okay. Yay. Okay. Now we want to look at just centered and different orientations. So it's not centered at 0, 0. So let's just put center at h, comma, k again. Okay. So the pictures this time, this thing will be centered at h, comma, k, and then we'll be going left and right by a, some a value. So the formulas for the vertices on the transversal will be h plus or minus a, comma, k. It's because you're going left and right. And then the foci will be at h plus or minus c, comma, k. Right? So the foci go outside of the vertices. And then the vertices on the conjugate axis will be at h, comma, you have to go up and down to get to those, right? So you go up b and then down b. So it'll be at location h, comma, k, up or down by b. Okay. So let me go ahead and draw the thing. So I'll use blue for the box and red for the isotopes. And then white for the branches. The formula for the isotopes this time, the formula will be, so you need a point, right? So the point this time is h, comma, k. So this is for the asymptote work. And then you need a slope. And in this orientation, you're going up by b and then over by a. Or you're going down by b and over by a. So from the formula, y minus y1 equals m times x minus x1. And let me just kill both birds with one stone by putting plus or minus b over a. That way, if you're going down, it's minus b over a. If you're doing the up asymptote, it's plus b over a. Okay, so you're going to end up with y minus k equals plus or minus b all over a times x minus h. And then your formula will be y equals plus or minus b over a times x minus h plus k. All right. And on a test, I would give you these formulas. It's just not worth memorizing those. But the formula for this hyperbola with a shifted center will be x minus h squared all over a squared minus y minus k squared all over b squared, and that'll equal 1. Okay, and then we want to look at the other orientation. So again, the centered at h, comma, k. This time for the, sorry, I just belched, I didn't mean to. For this orientation, the vertice, stupid pen. Okay, so the transversal vertices, you have to move up and down to get to them by A, right? So those are going to be H comma K plus or minus A. Then the foci, H comma K plus or minus C, right? So those will go on the outside of the vertices. And then for the conjugate sort of vertices, you're moving left and right by B, so it'll be H plus or minus B comma K. So there and there, and then we could do a box on it. And then we do our isotopes. And then we do our branches. Okay. I need formulas for the isotopes. The formulas for the isotopes would be just like the same construction as before, except instead of B over A, it'll be A over B. Okay, so the isotopes, I'll just write those out here. So Y equals plus or minus A over B times X minus H plus K. All right. And then the formula for this orientation, the Y will come first. So Y minus K squared over A squared minus X minus H squared over B squared equals 1. Okay? Okay, so a lot of stuff there. Let's take a look now at graphing these things and getting all the information down. So problem 35, x plus 3 squared all over 25 minus y squared over 16 equals 1. Okie dokie. So the center, if you wish to do that first, negative 3 comma 0. And then we need our A, B, and C. So the A value is with the X, with the positive portion here. That will be 5. The B value will be 4. And then the C will be the square root of 25 plus 16, which is the square root of 41, which is about 6 point something. What else? You may want to get a sort of a picture going. We're at negative 3, 0, so we're kind of going to be in the second and third quadrants. Okay, so negative 1, 2, 3, 0. The transversal axis is actually on the x-axis, so we'll be, for our vertices on the transversal, you're going left and right. So it'll be negative 3 plus or minus 5 comma 0. So 1, 2, 3, 4, 5 is one of the vertices. And then we need to go a little bit more for the focus, 6, 7, so that'll be in before in there. 1, 2, 3, 4, 5 for the vertex, 6, 7 in there for the foci. And then for the conjugate axis vertices, negative 3 comma 0 plus or minus 4. So you're going up and down by 4. 1, 2, 3, 4. 2, 3, 4. Okay, so you got a guy up here and a guy down here. Then you need your box. I'm doing it in red. My box is a little lopsided. Get your isotopes. So the isotopes like this. And then I guess you get your formulas for your isotopes. You want them right now. So in this orientation, you're going up by B and over by A. So Y will be plus or minus B all over A times X minus you know, the x coordinate for the center, which is -3, so that would being x plus 3, and then plus 0. So we'll just leave it at that. So what is the b and the a? So b is 4, a is 5, and then x plus 3. Okay, so it's the isotopes, and let's get the branches drawn on now. Okay. Okay. Okay, so completing the square problems, we saw those with the ellipse. You're still going to see them here. So for completing the square. So in general, when you're dealing with these creatures, you'll be presented to them in this form out in the wild. Okay. If it had another variable like z, like if it was on this side, z was on this would be a three-dimensional object. You'd have to figure out what the heck it was just by kind of completing the square maybe and doing some other jazz. But to get a picture, what you do is let one of the variables equal 0, and that's equivalent to kind of taking a cross section and looking at a cross section. Then you construct the object from the cross sections. Okay, so in general, we would let one of the variables like z be 0. So I'm talking 3 dimensions here. If you're in 3 dimensions, we don't do that, but if you kept taking math, you eventually would. So just kind of hoping to give you some motivation for why we do this. But anyways, we would want to see what this cross-section was. It will be a hyperbola, and then from that we could kind of figure out the type of three-dimensional object. They have these things called elliptic hyperboloids, and they have cross-sections which are hyperbolas. So anyways, back to reality then. How do we do this? We're going to group the x terms together and then factor out the 16. Group the y squares together and factor out a -1 from those, and then push all the constant terms to the right hand side. Okay, so 67. Okay, so I'm factoring out the 16, x squared plus 4x, and then I'm going to complete the square, factoring out the minus, that'll be y squared plus 2y, and then I have to complete the square there. And then on the other side, I got -67 plus something plus something. Okay, so the thing, it's b all over 2 squared. So in this case, b is 4. 4 over 2 is 2. 2 squared is 4. So I'm adding 4 in here. And then the other guy, 2 all over 2 squared is the same as 1 squared, which is 1. Okay, on the other side, you can't just add in 4 and 1, right? We talked about this in the last video. It's actually what you've added in is 16 times 4. If you kind of think of this, if you were to distribute that, you would have a plus 16 times 4 floating around on the left-hand side that wasn't there before. So you're not adding in 4 over here, you're adding in 64. 16 times 4. Okay, and then you're not adding 1, and lastly, you're adding in -1 for the same reasons. Okay, so now factor, so 16 times x plus 2 squared minus y plus 1 squared equals -67 plus -1 is -68 plus 64 is -4. Okay. We're going to want to divide everything by -4, so we'll end up with -4 all over x. So 16 over -4 is -4 over 1. So -4 plus times x plus 2 squared all over 1 plus y plus 1 squared all over 4 equals 1. Then we're trying to get it into our form. So the positive part, we want to put that first. So y plus 1 squared over 4. And then minus this other thing, but we want to write it with without that pesky 4 sitting up in front. So you may remember that the kind of trick is to say that 4 is the same as 1 all over 1 over 4, right? So that's what I do. I rewrite this as x plus 2 squared all over 1/4. And then set that equal to 1. So now I can go ahead and find my ABC values. A is 2, B is 1/2, C will be the square root of 2 squared, 4, plus 1/4. That's going to be 16/4 plus 1/4. That'll be square root of 17/2, and that approximately is 2.06. Okay, this time the branches of the hyperbola will be oriented on the, I think I'm going to need to move that axis a little bit. We're going to be oriented parallel to the y-axis for the transversal, so the branches will be kind of up and down, I guess. Okay. The center, I guess I didn't identify that yet. Might as well do that. It'll be at -1, -2. So it'll be in the third quadrant, -1, -1, 2. Maybe you need a little more room downwards. What else? The vertices then on the transversal will be -1. We have to move up and down to get to those, right? So it'll be plus or minus 2. So you go up 1, 2, down 1, 2. The foci, same sort of game. You have to move up and down. So -2 plus or minus root 17 all over 2. So -2, 1, 2.06 about, 1, 2.06 about. And then for the vertices on the conjugate axis, you're moving left and right by 1/2. Okay. So I go 1/2 over here, 1/2 over here. Then I can get my box. Then I could get my isotopes. Then I can get my branches. Whoops, I want to do my branches in white. Move the page there a little. I need formulas for my isotopes, potentially. So y will equal, so this time the slope of the thing will be up A and then over B. So plus or minus A over B, which will be 2 all over 1/2 times x minus -1, so x plus 1 plus -2, so minus 2. Let's rewrite that a little bit. So that is just be 2 over 1/2 is the same as 2 times 2, which is 4. So y is plus minus 4 times x plus 1 minus 2. And I think that'll do it. You know, is that all they need from us? You guys need any more? You want anything? All right, so the application, and I'm yelling at the book, not you guys. Does the book need anything more from me? You know, I was a student once too. Okay, so anyways, applications. For this application, we need that 1 mile is 5,280 feet. And this is an interesting application. I don't know if this is how it's actually done because I've never been. I've never had any experience with this sort of thing. But what's going on is you have 2 listening stations on the shore, so that there's water out here. To pretend the x-axis is like the beach, and on the beach there are 2 listening stations sitting here and sitting here, and then there's an explosion out here somewhere in the water. So maybe a ship explodes or a helicopter crashes or something like that. And then the listening stations can tell what time they hear the explosion. Okay. So listening station M1, we'll call it, will hear the explosion 2 seconds before listening station M2. And from that information, you could kind of figure out a location, okay, believe it or not. So first off, note that sound travels 1,100 feet per second. Okay. So the difference between M1 and M2 was, we want to kind of know the difference in location. And because M1 hears a sound 2 seconds before M2, we can kind of figure out that distance, the difference between the distance from M1 to the explosion and M2 to the explosion. So recall distance equals rate times time. So in this case, the rate that sound travels is 1,100, and then the time difference between the two is 2, so we have 2,200 feet. So if you go PM1, the distance between, we'll call this P, and the difference between PM1 and PM2 must equal 2,200 feet. And this is good because if you remember, and maybe we should put some absolute values on there, if you remember, that was the definition for hyperbola way back in the beginning. You've probably forgotten by now, right? But there it is. That equals 2a. So we could set that 2,200 equal to 2a. And then we have our a value. A is just 1,100. The book notices that the difference, or the distance between M1 and M2 is 2 miles. Okay, I think. No, they're 1 mile apart. Sorry. So 1 mile is, you got to be a little careful with the units. 1 mile is 5,280 feet. So what does that tell you? Well, you can look at these guys as foci, right? So the C values are what you're getting from that. So C must equal half of 5,280, right? So that will equal, I think, 2,640. And from there, you can get the B value, because we have this relationship C squared is equal to A squared plus B squared. And so, 2,640 squared is equal to 1,100 squared plus B squared, and then solve for B. So B will equal, at the end of the day, square root of 2,640 squared minus 1,100 squared, which turns out to be some obnoxious number, 5759600. And then from there, we can create the equation of a hyperbola, and that will kind of tell us at least what direction for maybe our helicopters to go in. So at the end of the day, the explosion is on the right branch of the hyperbola given by the formula x squared all over a squared, which is 1,100 squared, minus y squared all over b squared, which is that nonsense that we just figured out. Okay, so this would be, actually this is this, it should be the square root of this. So when I plug it into the formula, it'll be just the 575,960, and that'll equal 1. Okay, so it's really cool that you could, I don't know if that's how it works for these people, but you can kind of get an idea of exactly where to point your helicopter in, which direction to point your helicopter in, if you just know some minor details. The time of the explosion, so you need a really good clock for one thing. Then the distance between the two listening stations, which obviously they would know that. I don't know about the clocks, and then having a recording. Maybe you'd have to have some seismic counter out there, like one of those little machines that records sound, activity plus time, and then maybe that would be a realistic option for this. But anyways, a cool application in my opinion. And that'll pretty much, I think, do it for this section. Okay, so as usual, thanks for watching, and we'll see you next time.